Welcome to my Physics 2211 Lab 2 video. So in this lab, we're graphing three models. First is the observed tracker data, second is the computational data, and then the third is the computational data with the expected drag force. So in order to do this, I crumpled up a piece of paper towel and it was dropped from an initial height of 1 meter with no initial velocity. And the goal is to quantify the effects of drag and gravity on a free-falling object that started with no velocity. And then we wanted to graph this and then compare those results. So the main result I found was that by incorporating a drag constant into a computational model, we can expect more accurate set of results. So the principles in use include Newton's second law, the weight force, and the drag force. Those are all the equations, and I'll get more in depth into them as I use them in my computational model. Here's free body diagrams and key assumptions. So as you can see on the left, there is a force of gravity pulling it down and then a small amount of drag pulling it up. And that's almost the first few frames of the video. And then as you can see, as time moves on, the drag force increases and Fg increases as well. And I'll talk about that in a little bit as well. Key assumptions is that there's only movement occurring in the y direction. M equals mass, Fd equals force due to drag, Fg equals force due to gravity. The system is the paper ball and the surroundings are everything else. So here's the video of the tracker data. As you can see, the video started with a crumpled piece of paper up there and I dropped it and went down. These are all the data points that I recorded with a change in time of 0.0335 seconds. And then here is the graph that it spit out. My mass is 0.0045 kilograms, and then the initial and final velocity or position are right there. Here's the computational base code. So as you can see, I have my ball mass right there, 0.0045. My initial position vector, it's almost close to 0, but I just wanted to be more accurate, so it's negative 0.019. My delta t I changed to 0.0335 just to make each time step more accurate so it lined up with my actual tracker data. And then the j hat vector is just 0, 1, 0. So as you can see here, we have I only have Fnet equals Fg. That's important because this model isn't taken into account drag. And then as you can see, Newton's second law is put in here because the net force divided by the ball mass equals acceleration, which in this case is just gravity. And then below here, my change in position is that change in the velocity times delta t, and then that updates the position. So as you can see on the left, this is the graph that it spits out. Position is constantly changing on this sloped line, whereas the velocity is constant because gravity is constant. So here is the computational model with the drag. All we change here is that b equals 0.003, and b is the drag constant. So I had to do trial and error to see what lined up better with the observed results, and 0.003 was very close. So here now we make Fnet Fg plus F drag. So F drag equals the negative b velocity squared times the j hat that I talked about before, and then Fg is the same. So then that's then changed into here with Fnet divided by the ball mass equals acceleration, because now this includes drag. So here are the representative arrows. So without drag, you just have gravity pulling down, whereas with drag, you have a force pulling upwards as well. So it's going to counteract the gravity, not by much, but by a certain amount. So here's the model. So as you can see, the blue is the observed, red is with no drag, and yellow is with drag. So yellow and blue, or the with drag and observed, are very close, and then the no drag, obviously it's going to go lower. And these are all my data points. So some discussion. So errors in the experiment can be changing in placing the point mass with each frame. I tried my best, but it is a human error. There's no account for movement in the x direction. There's rounding inaccuracies, especially with the gravitational constant. And then there's also video distortion. So the first what does it mean question. Which model, if anything, predicts a terminal velocity? So the computational model with drag depicts a velocity graph with a slowly changing slope, indicating that an asymptote will be reached, and therefore this model predicts a terminal velocity. So up here, velocity is constant, so this will continue to decrease forever, whereas this, as you can see, it begins to level out, which is predicting a terminal velocity. So my second half of that question then is, imagine if the object was initially thrown downward, would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So I modeled this by changing the initial velocity to -1, and then by changing the initial velocity, we can object the model thrown downwards. And a terminal velocity is still indicated to be present with the initial velocity. And we see that it just simply reaches that terminal velocity a lot faster than the free-falling object.